want to have a brief look at inodes and how they're used on a Linux machine. First command, let's look at is df minus I. This shows us, normally if we do df, shows us our disk free space, or how many blocks we have free. But as you do the df minus I, shows us how many inodes we have free. In a previous discussion, we said that every file is referenced by an inode. However, if you create a lot of small files, for example, here on my home directory, I could create a lot of small files, but I only have a finite amount, 262,144 small files. And I could exhaust that before I actually exhaust disk space if they were all really small files. But anyway, currently I'm using that many. Let's just see what happens if I create a new one. Now I am in my home directory. If I do a df on dot, you can see /home is mounted on SDA3. And if I do df minus I on dot, it shows that I've used 17 inodes. So I'll create another file. Do that again. Now I've used 18. Let's create one more. And you can see I've used 19. So I've used up 19 inodes. Let's do ls minus li on this directory. So this is our inode number. Our inodes are referenced by a number. And so one of the interesting things also to look at, foo, that the stat command does access inode metadata. Some of this is metadata that the inode keeps track of. One of the most helpful things for me to understand inodes is by doing a hard link and maybe even a symbolic link. So let's just do a hard link first. So my target there is foo.txt link to foo. This will be my hard link name. Okay, so now if you'll look at this, this is interesting. So link to foo references inode ending in 79, and foo references inode ending in 79. Let's add some content to foo.txt. So you can see that's in there. And since that references the same inode, which in turn points to the same data blocks, we get the same data when we cat that out. That's how a hard link works. If I were to remove the original file, can I get to my data blocks still? Well, sure, because we have an entry in our file system table that maps to inode ending in 79. However, if we now let's do a symbolic link to bar.txt. So we'll just call this symlink. You can see now that this word symlink simply points to the file name bar.txt. Let's do ls minus li. Bar.txt is an entry in the file system table that points us to inode ending in 80. Symlink is an entry in the table that points us to, well, it's an inode ending in 81, but it really says go access the file name bar.txt. So let's just hello, and we'll put this in bar.txt. So we cat out bar.txt, we cat out a symlink. Right now there's no big major change in the way that these links differ. But now if I remove bar.txt and we try to cat out a symlink, you will see that it doesn't work anymore. This link in this particular instance turned black because it's still pointing to the file name. So a symbolic link points to the file name, whereas a hard link points to the actual inode. And the last thing that maybe I'll say real quick is notice I have two partitions here. Inode numbers only have to be unique if they're on separate partitions. So let's go to our root partition and do a df minus I. So, actually minus LAI. That's what I meant to do. You can see I have inode number 2 here. Always takes me, and notice I'm in the root of my file system. Inode 2 can't get any higher than root, so it says if you do a cd dot, take us to inode 2. If you do a cd dot dot, well, you can't get any higher still, so take us to an inode of 2. However, look here at home. That also has an inode of 2. Why? Well, just what I said. Inode numbers can be reused if they are on different partitions. Well, what's this 2? Well, it's on dev, and dev is actually it's on a different file system. So as long as it's on a different file system or a different partition, you can reuse the file number. So that's important as well.